Yes, I'm Paolo Bettotti from University of Trento, and today I will show you our latest result on the fabrication of a polarimetric sensor based on nanoporous thin film membranes. That's the outline of my presentation. I'll start giving you some number about the food allergy problems in Europe, at least with the number, why we want to create a point-of-care detection system. Then I try to convince you that porosilicon and porous material in general are good candidate materials to fabricate such kind of detectors. I will show you the advantages that our polarimetric approach has compared to the usual Fabry-Perot cavities. And then I will show you some experimental results about the sample optical quality and the state-of-the-art sensitivity we recently reached. So, food allergies and point-of-care diagnosis. Well, the research program is funded by European Commission under the 7th Framework Program. And the number I put here, food allergies affect 1–2% of adult population in Europe, but in children it can reach value up to 10%. That means that nearly 15 million people in Europe is affected by food allergy disease. It is a big problem. So probably you know there are two types of analytics for detection of food allergies. One is the skin prick test, where you directly test the allergen on the skin of the patient, and the other is the laboratory detection, that is a long time consuming analysis. We want to realize a lab-on-a-chip solution for this problem that is able to start from a single drop of blood, prepare the sample, do the analysis in a very short time. And to do that, we think that the optical detection system is the most suitable, that gives very high sensitivity and can be easily integrated into a multiplexed approach. So just a few words about porosilicon. Porosilicon is a type of nanostructured silicon that you can easily get from a silicon wafer. You place your silicon wafer in an electrochemical cell, you force a current or a voltage, depending on the condition, and with hydrofluoric acid as etchant. And at the end, you get this nanoporous sponge, where pore size can be tuned over a very broad range of size, starting from few nanometers only up to micron size. And these are two STM images that show two different samples with 60 and 100 nanometer average pore size and different porosity. The structure is highly anisotropic. Pores are straight channels that do not interconnect to each other. And the pore size is proportional to the applied current. That's why porosilicon becomes quite famous, because you can create this periodic structure with low and high porosity layer. This is a so-called Bragg mirror. It's a dielectric mirror that has very high reflectivity in well-specific wavelength ranges. This is a zoom images. And if you play with the current during the etching, is it possible to completely detach such thin membrane and transfer to some other substrate? This is an image of a very thin membrane. This membrane is 3 micron thick only, and is nearly 1.5 centimeter, and it was transferred onto a microscope or glass. So up to now, porosilicon was investigated by the possibility, mainly because of the possibility to make these nanocavities. That means that you etch 2 mirrors, and in between you put a defect layer, the so-called defect layer. So if you look at the response of this structure, then you will see a very high reflectivity band with a dip in the middle because of the presence of a layer, of the defect layer. Now, if you want to build a sensor on this type of structure, the idea is that if something enters into your device, the refractive index will be affected, and this is translated into an optical shift of the cavity peaks. That means more things enter into your sensor, the greater will be the optical shift. But there's a problem. We can make very high sensitive sensor with this approach, but if you want to make a point-of-care detection system, that means it's a robust and compact device where the doctor push a button and wait just for the answer of the analysis. This approach requires a careful optical alignment system, and it's hard to implement this in a robust device. So we change our approach. We look at the polarimetry. Now, if you consider an elliptical pore, then the horizontal and vertical polarized light feel a different structure. That means that the refractive index of the horizontal and the vertical polarization will be different. That means that we are created a birefringent material, okay? And you can say, yeah, but you show us that pores are nearly circular in porosilicon. That's true, but if you look at to a circular pore under an oblique incidence angle, it becomes an ellipsis. That means that also porosilicon can have a birefringent form, and we can detect variation due to the binding, for example, of specific proteins by looking at how these birefringence change, and this birefringence change is translated into a dephasing effect. So our colleague in Valencia built up an optical setup. There's a tunable laser source, polarizer. This is a photoelastic modulator that sinusoidally varies the polarization of the light. Porosilicon sample is placed here in between. And if you do a wavelength scan of this type in this type of experiment, you get such an interferometer, and you see that if you have air, isopropanol, or ethanol in the pores, you see different type of interferometer. From this data here, we can extrapolate the birefringence of the material, and if we consider the air case, we have a birefringence that tends to 0.14, which is pretty high. If you consider the calcium carbonate is 0.26, if I remember well, that is one of the most one of the material with the highest birefringence. So we start to do the optical analysis of our sample. This is a cross-sectional images of a porosilicon layer. You see the pore that grows mainly along the 100 direction, and in our first experiment, they are heavily branched. Nevertheless, we check the sensitivity of this type of device, and we notice a very large sensitivity. For example, at 1.5 micron, we get a sensitivity of 1.2 micron per refractive index unit. That means that if your refractive index changed by a single unit, your spectra will be shifted by 1,247 nanometers. This is a huge value comparable with photonic crystal nanocavity and also surface plasma resonance methods. But we noticed that the experimental response was much lower than the theoretical one. So we start to analyze the effect of this branched pore here. And we see that this pore has a great effect, has a big effect on the depolarization of the light. So the surface, the roughness of the surface induces a great light scattering, big light scattering that depolarizes the light and limits the sensitivity of our sample. Then we improve the etching method, and from such a highly branched structure, we are able, by modifying the etchant composition by adding some oxidant, we are able to greatly reduce the roughness, and pore becomes much more straight pore with smoother surface. We perform a fractal dimension analysis, and we check that the fractal dimension decrease because the etching reduce the surface roughness of the pore, within the pore. I was too fast. So now we measure again the optical properties of our membrane. Here is reported one example of the analysis. In this case, we perform a variable angle spectra, which is equivalent to wavelength spectra. And also in this case, you can see that porosilicon, the response with air in the pore, within the pore, or with water or ethanol are different, but all these responses show birefringence effect. Now here, I compare the optical birefringence between two different membranes, a thinner membrane, 13 micron thick, and a thicker membrane, which is 30 micron thick. In the previous generation, the first generation of sample without the oxidant, we noticed a certain amount of birefringence, which was pretty high, but with improved etchant composition, we are able to increase the birefringence value by a factor of 50% for the thinner membrane, and we are nearly duplicating the birefringence value for the thicker membrane. We are now conducting experiment to measure the effective sensitivity of this new improved sample, and we expect to nearly double the sensitivity. So the conclusion, we have improved the method for fabricating freestanding porosilicon membrane, and we show that it's possible to obtain very thin, high-quality membrane also on medium and type doped substrate. This is the first time people create this type of sample. We have characterized the membrane optical birefringence and found state-of-the-art sensitivity. And we achieved this nice result because we improved the etching method, and we are able to greatly reduce the roughness that in turn reduce the polarization factors of the sample. Obviously, this is a research performed within a research program that has several partners, and I would like to acknowledge all of them. Thank you very much.